No matter how it's built, high, wide, plain, or fancy, concrete is made of 4 basic materials. Coarse aggregates such as gravel or crushed stone. Fine aggregate of natural or manufactured sand. Portland cement and clean water. These materials will produce good concrete, sharp in detail, strong, durable, or poor concrete. The difference in quality depends on how you select, how you proportion, how you mix, how you transport, how you place, how you finish, and how you cure this mixture of common materials. Anyone who uses clean, sound materials and follows a few basic principles can make quality concrete. If you could look deep into good workable concrete, you would see millions upon millions of pieces of inert material. Each piece, no matter how large or small, is entirely surrounded by a chemically active paste made of Portland cement and water. The aggregate is uniformly distributed. The larger pieces of rock separated by smaller pieces, which are in turn filled in with sand. And finally, sufficient water cement paste fills all the remaining voids. The aggregate occupies about 3/4 of the concrete mass. Aggregate must be of the best quality. The aggregate used in making concrete ranges in size from small rocks to sand grains. The best aggregates are clean, sound, rounded gravel, roughly cubical crushed rock, or manufactured aggregate such as slag, such as expanded clay, or such as expanded shale. Sand must be clean, cubically shaped grains. Brittle stones are weak and produce concrete of low strength and durability. Soft particles absorb water when wet and lead to pop-outs when frozen. Dirty aggregate coated with clay or organic material that will seriously impair bonding with the cement paste should be rejected or used only after thorough washing. Fine and coarse aggregate within a specified range of gradation sizes are used on construction jobs. Between the pieces of similar size, poorly graded coarse aggregate, there are large spaces or voids. To fill these voids requires a large amount of cement paste. This is indicated by the amount of liquid needed to fill the voids. Well-graded fine and coarse aggregate, as in this beaker, reduce void spaces to a minimum. This is shown by the small amount of water necessary to fill the voids. Good concrete is a combination of sound aggregates bound tightly together by the hardened cement paste. As the aggregate is essentially inert, it is the quality of cement paste acting as a binding agent that largely determines the strength, water tightness, durability, wear resistance, and other desirable characteristics of concrete. Cement paste is a blend of Portland cement and water, which forms a semi-fluid paste that eventually hardens and binds together the aggregate in the hardened concrete mass. If you magnify a particle of cement many thousands of times, you will see the water and cement chemically react rapidly at first, then more slowly, until virtually all the cement is combined with the water. This process is called hydration and continues as long as moisture is present and temperature is favorable. In the paste, particles of cement hydrate at the same time to form new gel-like substances that harden and strongly interlock, binding the aggregate together into a rock-like mass. The proper ratio of water to cement making up the paste is essential to quality concrete. Only enough water is used to make sure that the mix will have adequate strength and durability and be workable enough to be placed and compacted in its final location. As water is added, the cement particles tend to separate. The ratio of water and cement must be carefully controlled to obtain a mixture that will develop sufficient strength and impermeability to do the job. Extra water that does not combine with the cement eventually evaporates, leaving pores and capillary passages that reduce water tightness, durability, and the strength of the paste. To illustrate this, cylinders of hardened paste were each made with the same amount of cement, but with different amounts of water. They all weigh approximately the same, since the water not combined with the cement has evaporated. In the shorter cylinders, the cement gel particles are bound closely together. In the longer ones, they were spread apart by excess water, which has evaporated, leaving a honeycomb of voids. 2 test cylinders were cast out of 2 different batches of concrete containing identical amounts of cement but different amounts of water. The first was made from the batch with the same high ratio water to cement as the long paste cylinder. The second was made from the batch with the same low water cement ratio as the short cement cylinder. Compression testing proves that strength varies with the amount of water used with a given amount of cement. This relationship between water and cement, the water-cement ratio, is expressed in terms of pounds of water per pound of cement. The cylinder made with a low ratio of water, 0.40 pounds per pound of cement, tested 6,000 pounds per square inch. The cylinder made with more water, 0.70 pounds per pound of cement, tested 2,900 pounds per square inch. From such test results, a curve is plotted which can be used to determine the water-cement ratio required for any strength. For example, to obtain a 5,000 psi concrete at 28 days with these ingredients, use a water-cement ratio of 0.49 pounds of water to each pound of cement. To study the effects of natural weathering, the Portland Cement Association, in cooperation with various government agencies, built thousands of concrete specimens. These were subjected to snow, rain, sunshine, hail, and freezes from early 1941 until the conclusion of the test in 1966. Results of these studies, completed after 25 years of exposure, showed that intentionally entrained air in cement paste improves the durability of concrete. These 2 concrete boxes represented miniature retaining walls. The concrete used in these boxes was identical, except that the one on the left contained entrained air, which made the difference between the endurance and the deterioration of the concrete. The use of a chemical agent, which may be ground with the cement or added at the mixer to intentionally entrain air in the mix, develops millions of tiny air bubbles in each cubic foot of concrete. These act in the same manner as ball bearings and make it more workable. The bubbles also provide minute pockets for the expansion of trapped water during freezes, easing pressure on the concrete and improving its durability and resistance to surface scaling. Under a microscope, you can see the outline of the entrained air bubbles. Those at the left appear as depressions or pockmarks. This concrete has about 5% entrained air. The concrete at the right has very little air. Concrete pavements face some of the most severe exposure conditions, cycles of freezing and thawing, wetting and drying, plus the corrosive effects of heavy applications of de-icer chemicals. Each of these laboratory specimens, simulating pavement slabs, has been through 200 freeze-thaw cycles using de-icers mixed with water impounded on the top. The specimen at the left has no entrained air. The air content increases from left to right. From this and other tests, we can determine the optimum air contents for concrete subjected to a variety of severe exposure conditions. Total air content for 1 1/2 inch maximum aggregates should be 5 to 5 1/2%. For 1 to 3/4 inch size, 6% air. For 1/2 inch size, 7% air. And for 3/8 inch maximum aggregates, 7 1/2% air. The water-cement ratio affects more than the concrete strength. It affects all of the desirable properties of concrete. Concrete must be watertight, a quality essential for tanks, for pipes, for dams, for swimming pools, for seawalls and other structures subject to hydrostatic pressure and weathering. Water tightness depends upon the quality of the cement paste. The water tightness of concrete can be measured in this apparatus. Hardened concrete discs of different water-cement ratios are inserted in chambers and subjected to water under pressure for a specified time. Leakage through the discs is collected and measured. Discs with a low water-cement ratio were watertight in 7 days. Discs made from a mix with a high water-cement ratio still showed leakage after 14 days of curing. Concrete floors and pavements must stand up under heavy and continual traffic. Concrete, therefore, must resist wear and abrasion. Abrasion resistance is difficult to measure, but relative values can be established. A specimen is ground under rotating steel balls loaded to a constant weight. The specimen is weighed before and after the test. The weight of concrete worn away in a specified number of revolutions indicates the wear resistance of the concrete. These specimens show how the water-cement ratio affects wear resistance. Concrete made with 0.80 pounds of water per pound of cement shows severe wear. Concrete made with only 0.45 pounds of water per pound of cement survived the test with little wear. The strength of concrete at any water-cement ratio is improved by increasing the curing time. Concrete is cured by being kept moist at reasonable temperatures for as long as it is practical. As long as moisture is retained and the temperature in the concrete is favorable, the cement will continue to hydrate. Tests made at various ages show that concrete will continue to gain strength as long as it is cured. To study the effects of hydration, laboratory specimens are cured in moist rooms under controlled temperature-humidity conditions. Air-entrained concrete made with a water-cement ratio of 0.50, 1/2 pound of water per pound of Portland cement, will typically show a strength of about 2,000 psi after 7 days curing. The 28-day strength will be around 3,500 psi, and at 6 months, 4,500 psi if the concrete is continuously cured. If curing is stopped and the concrete allowed to dry, there is very little further strength gain. Concrete test specimens cured only 7 days level off at about 3,400 psi. Concrete specimens exposed to air after 3 days of curing reach a maximum strength of only 2,800 psi. Concrete that is not cured at all gains only slightly more than 1/2 its potential strength. Concrete can be cured by keeping it continuously moist under wet burlap, under waterproof paper, under plastic sheets, or by sealing the surface with a membrane-forming curing compound. Remember that the longer concrete is cured, the stronger and more durable it will become. 2 additional factors, workability and finishability, should be considered when applying these principles to the design of a concrete mix. Workability is that property which determines the ease with which the concrete can be placed and consolidated without excessive segregation and bleeding. Finishability relates to the ease with which the surface of the concrete can be worked with finishing tools. Concrete made with too much water will flow easily, but the paste separates from the coarse aggregates, which tend to settle out and collect at the bottom, a condition called segregation. A mix as sloppy as this will result in poor, non-uniform concrete. The bleed water that appears on the surface is caused by the settlement of solids in the mix. As the aggregates settle to the bottom and the water rises to the surface, it leaves channels or pores in the concrete. Worse yet, bleeding increases the water-cement ratio at the surface, weakening that portion of the concrete that takes the most wear and weathering. This mixture is quite stiff. When deposited, little segregation occurs. There may be some bleeding, but it will be much less than with a sloppy mix. To minimize segregation and bleeding, use the stiffest practical mix of concrete. This is a plastic, workable mixture of concrete with an air entraining agent added. There is no segregation or bleeding, and the mix looks and feels buttery. The qualities desired in fresh concrete are established by its intended use in service. These are included in the drawings and specifications by the architect and engineer. They are translated by the contractor's concrete supplier into economical quantities of properly proportioned materials that go together into a workable mix. Fortunately, the quality controller or concrete technician has manuals prepared by the Portland Cement Association and other agencies, which contain tables and charts to help him set up trial mixes of concrete to meet any requirement. The following example illustrates the fundamentals of quality concrete mixture proportioning. Problem: design a mix for a 10-inch thick concrete retaining wall to be built in northern Wisconsin, a region of widely varying temperatures. The wall, which will carry no vertical load or impact, can safely be designed for 3,000 pounds per square inch. The 28-day water-cement ratio strength table for normal concrete shows that 0.68 pounds of water per pound of cement will produce this concrete. But to complicate matters, this wall must withstand some hydrostatic pressure, and worst of all, be exposed to salt spray from passing traffic and severe weather where temperatures can range from 25 below to 90 above. The first helpful table says that structures in severe climates must use air-entrained concrete and should be designed with no more than 0.45 pounds of water per pound of cement. While this will produce a stronger concrete than required, the water-cement ratio is always dictated by the most severe conditions the structure will face. For economy, use the least recommended amount of cement per cubic yard of concrete. Again, the proper table is handy. It shows that the amount of mixing water needed decreases as the size of the coarse aggregate increases. Since we must keep the ratio of water to cement constant, as less water means less cement, the largest practical size of coarse aggregate should be used. Aggregate size should not exceed 1/5 of the width of the 10-inch form. This indicates a 2-inch maximum coarse aggregate. However, a minimum dimension of 2 inches between the reinforcing bars and the form further reduces this requirement to a 1 1/2 inch maximum. The table of recommended air contents indicates 5 1/2% total air be entrained in the mix. Until past experience can serve as a guide, the slump or consistency needed to place and consolidate the concrete in the wall can be determined from a table. In this situation, a slump range of 1 to 4 inches is allowable. For this demonstration, we use 3 inches. Next, the mix design is tested by making a small trial batch using 25 pounds of cement as a convenient measure. To arrive at the proper amount of water, multiply 25 by 0.45 pounds to obtain 11.25 pounds of water. The air entraining agent is added to the water. For laboratory conditions, the coarse aggregate is saturated, then surface dried so as not to absorb any of the mixing water. Both Both fine and coarse aggregate are then carefully weighed in separate containers. All the cement is put into the mixer, then the water is added, and the two are mixed into a fluid cement paste. The coarse aggregate is added, then the fine aggregate. The two materials are added alternately until a workable mix is obtained. Not too grainy with coarse material or too mushy with excess sand. Standard slump tests are made during mixing until the right amount and proportion of materials have been added to produce the desired workability at the recommended slump of 3 inches. When the desired slump is obtained, the remaining portions of the aggregate are reweighed to determine how much material was used. "87.3 pounds of coarse aggregate, 56 pounds of sand. The total weight of the trial batch after adding the weight of cement and water is 179.55 pounds. The air content of the batch is checked with an air meter to see that 5.5 plus or minus 1% air has been added. And finally, to translate this particular mix into cubic yards, the convenient quantity for ordering concrete on the job, half cubic foot units are measured out and weighed. The half cubic foot weighs 73.1 pounds. 1 cubic foot is then 146.2 pounds. This means that the batch using 25 pounds of cement, which weighed 179.55 pounds, divided by 146.2 equals 1.23 cubic feet. Since there are 27 cubic feet to the yard, 27 divided by 1.23 equals 21.95, the number of 25-pound batches needed to make a cubic yard. Thus, this mix of concrete calls for 21.95 times 25, or 549 pounds of cement per yard. 549 pounds of cement, 247 pounds of water with air entraining agent, 1,916 pounds of coarse aggregate, and 1,229 pounds of sand. Remember that the quantities determined in the lab will almost certainly require some adjustments in the field. Moisture content of the aggregate must be considered, as well as the presence of chemical admixtures and pozzolans. Temperature and humidity will have an influence, as will the size and type of mixer employed. Such changes as required will not affect the quality of the concrete, as long as the water-cement ratio is maintained. The result is quality concrete, designed to do the job. Quality concrete is made of clean water, Portland cement, and well-graded aggregate. Remember, you can make poor concrete with good materials, but you can't make good concrete with poor materials. The difference in quality depends on how you design, how you select, how you proportion, mix, and handle these common materials. When properly transported, carefully placed, finished, and adequately cured, the result is quality concrete. It is strong, it is enduring, it is sharp in detail, and it is economical. It is the careful attention which you pay to these simple and basic principles that will make possible all the things men will design and then execute in the world's most versatile building material, Portland cement concrete.